Hi, welcome to the ZP Developers Zone. We do this webinar every Thursday at 8 a.m. London time, and we do it really to sort of answer questions that have come in from people during the week. So this is a sort of technical webinar where we answer questions. So what I'll do now is I'm just going to jump into it a little quicker and just say we have our ZP Academy. You can get free courses on the ZP Academy. We have our webinars. This is an example of a webinar, obviously. Collaborations. Strictly speaking, this is really with universities, and it does help with the geographical region because, for example, we can do PhDs, etc., but it's often helpful if the government is able to partly fund. And we do promote jobs through this forum, and we also have our ZP Developer Zone, and of course we have our workshops. It's probably worth saying that quite a few questions have come in this week about wearables, electrodes, etc. So the next workshop will actually be in March, and I would recommend that people come there. If you see a link, by the way, I will put the links underneath the videos afterwards. I just want to say a quick hello to Aftab this morning. Hi Aftab, nice to see you. And I will go a little quicker. So we do our workshops, and these are 2-day workshops often, and actually they're extremely comprehensive, and I think people come away with a sort of real satisfaction from them. The next one will be on the 9th and 10th of March, and that will be in Norway. So, for example, we've got somebody coming in for the UAE, United Arab Emirates, for the next workshop, so it's quite international. So question number 1 this week was about, we want to make a wearable sensor. We want to measure lots of vital signs, including like heart rate, heart activity, body temperature. And they also have some biomarkers in there: hormone, oxygen, lactate, and CPK, creatine phosphokinase. So I will discuss that. Somebody else wanted to just sort of us to talk through the 6-channel potentiostat that we have. So it's probably worth saying that ZP will sort of, support through this forum people's questions around electrochemistry and around biosensors, in particular those that are using our potentiostat, for example. Question number 3 is about cortisol, cortisone, and melatonin. I thought it was really interesting. I sort of knew this, but I'd forgotten it, the relationship between cortisol and melatonin. So I will discuss that. Following a reaction or reaction monitoring of detritylation. So, for example, when you build up a oligomer or a sequence of bases, you often build them on a solid phase, and one of the steps in the sort of cyclics in the synthesis is a detritylation. And I'll talk about electrochemical monitoring or electrochemical techniques for monitoring that reaction. Also, question number 5 was really around gold electrodes. You'll find a nice contrast between question 4 and question 5, because in question 4 I will recommend some gold electrodes, and in question 5 I will recommend some other gold electrodes. And then question number 6, somebody just wanted a smaller pack size on platinum electrodes, and I will also highlight that. I mean, just in general, if you can avoid platinum, go for carbon. Platinum's so expensive these days. But moving along. Question number 1 was really about hormones: lactate, CPK, creatine phosphokinase. They were interested in measuring heart rate, blood pressure, heart variability, activity, oxygen saturation, and body temperature, and also markers like hormones, lactate, and CPKs. Now, first of all, it's worth saying that the ZP's technology is actually best applied to things like the biomarkers. I would say that, so many people out there can help with heart rate and blood pressure. These are off-the-shelf solutions. It's really the sort of chemicals that ZP would be best at: the oxygen, the lactate, the CPK, and the hormones. And I will discuss those now. It's probably also worth saying that going after a range of analytes like this, it really takes a bit of training. So I'd actually say, you definitely have to come to the workshop before you really embark upon this, so you can understand the science and technology behind what you're trying to do, even before you start trying to do it. And like I say, I'll try and put some links underneath the video so you can find those workshops. So oxygen saturation, hormones, lactate, and CPK will be the ones I focus on this morning. So just to say that I will link to these hormones a few times today, but we have some data here from a hormone that's not, I don't think it's so human related. It's called androstenone. This is linked really to pig production. This is a some data from a sensor for cortisol. This is probably a unique sensor in the world, and this is some data linked to testosterone, and this is a unique sensor also. In terms of finding that data, the cortisol, androstenone, and the testosterone, we have those on our websites here. And under oxygen and lactate, for example, we do have oxygen data. Again, the links will help me remind to put underneath the video afterwards. It's probably worth saying that the oxygen and lactate sensor, anyone who comes on our workshop, they get to make an oxygen sensor and actually test it themselves. So that's why I keep emphasizing the workshops, because I think it's actually quite hard to get your heads around, let's say, or understand these sensors unless you kind of come in person. So, but those two sensors, everyone who comes in a workshop makes an oxygen sensor and tests an oxygen sensor, and everyone who comes to a workshop gets to demo a lactate sensor. And then, as I say, the next one's actually not that far away. It's on the 9th and 10th of March. Correct. So it's probably worth saying that all of those sensors that you've listed, apart from CPK, are actually on our website. So it's probably worth saying that we've got direct evidence or experience with all of them. The only one we don't have on the website is this creatinine phosphokinase. But I just want to say something about this particular enzyme. So, what it's naturally doing in the world is converting creatinine to phosphocreatinine, and the kinase is converting ATP to ADP in doing that. So it's basically sort of phosphorylating this creatinine small molecule, creatine small molecule. I want to say that we do have an ATP sensor, so in fact we can actually do this, really no problems. It's probably worth saying, and I should have put a link to it, that we have a concept called proof of principle. So if there's a sensor that somebody wants but is not on our website, then for example, with this one, it's the creatinine, or actually they want the enzyme sensor, the CPK. Then we know how to do it, and we can actually we can repurpose our ATP sensor to actually do it. So I would say that everything on that list is something we've done or we're doing. I'd say your first step is actually, I would really strongly suggest you come to a workshop, really to understand this technology. But know that we've either done them, they're either available on our website, or in fact, with the last one, because it's an ATP dependent sensor, we already have an ATP sensor out there, so we can repurpose that one for that work. Question number 2. This is somebody was just we've recently launched this 6-channel potentiostat. It's probably worth saying that if you're interested in our electrodes and our biosensors, etc., then I would strongly suggest, obviously, this 6-channel potentiostat, because actually we do most of our development, all of it nowadays, all of our testing on this particular potentiostat. As I say, this one's 6-channel. It's particularly small. You've obviously got the cables are in the back of that. Here we're using it one of our screen printed electrodes. I think it's question number 5, which was asking about gold electrodes, and it's probably worth saying that the form factor of this electrode that I'm holding in my hand will be exactly the same as that gold electrode. So just to kind of say that we're definitely shifting to doing a lot more technical support in these webinars, particularly around our 6-channel potentiostat. So what's good about it is its size is pretty good. The fact that it's developed specifically for electrochemical sensing, electrochemical biosensing, and the fact that the biggest users of this instrument is actually ZP, which really sort of helps us maintain our quality of this. We have had incidents in the past where, because we are ISO 13485, but in fact I don't think any other manufacturer of a potentiostat is ISO 13485, people tend to change parameters and hardware a little bit haphazardly. That can affect your results and you wouldn't even know about it, especially on these firmware updates. And I should say I could put a little link, and I'll make sure I try to put that link underneath the video as well. This is really interesting. Somebody wants to measure um, some hormones, melatonin, cortisol was what they were interested in. But I also made me just make a little check on cortisol versus cortisone, because sometimes people come to us with cortisone, sometimes they come to us with cortisol. And I just wanted to make an important distinction here that cortisol and cortisone are really closely related. I'd almost describe the cortisone as the oxidized version and the cortisol as the reduced version. I mean that because cortisol has this alcohol group, and if you oxidize an alcohol, you have the cortisone. This person was very kind, and they reminded me really that there's meant to be a link between melatonin and cortisol. So melatonin is a sort of pigment in the skin, and as the melatonin goes up, the cortisol goes down. So they've asked us to do a little bit of work on this. We'll try and slot it in when we can. I did say to them, yes, we have cortisol sensors, and we make those cortisol sensors available really on project work with clients. And I've put this up earlier on that we've actually got quite a lot of hormone experience. But also, and I mentioned the cortisol data, it's probably worth saying that cortisol technology we have is actually quite advanced, because we have an entire package for measuring cortisol, because one of our products under development is measuring cortisol in fish. There's many, cortisol is kind of known as the stress hormone. There's many scenarios where human and actually veterinary, where you want to measure stress, and we actually have a whole package for measuring cortisol, for example, in fish. I just want to touch on melatonin, because melatonin, this is the structure here. At ZP, we do actually have a skatol sensor, and skatol and melatonin have a really similar structure. I think what I'm looking at here, they call it a tryptophan. I'm pretty sure that's called it's called a tryptophan. So there's a tryptophan ring in skatol, and there's a tryptophan ring in melatonin. So I just want to make the point that this person's interested in melatonin. Actually, I suspect we could reposition the skatol sensor to also do melatonin as well, and I'll put a quick link underneath that as well. Question number 4 is really about if you're building an oligomer. I think the system is done by essentially immobilizing bases onto solid phase supports. Then they activate these bases, and they attach the next base, and then they attach the next base, and they attach the next base. Part of that, there's a little bit of chemistry called a trityl group or trityl group is put onto an alcohol, and then it's later on removed. Now, I personally have a little bit of a background actually in organic synthesis and flow chemistry, and also flow synthesis, including flow electrochemistry. So I've just kind of sketched out, the way I'm imagining that what needs to happen here is that you have what they call beads or solid phase supports. On there, you've got an oligomer, and at the end of that oligomer, there's a trityl group, and that needs to come off. So what people are doing is they're releasing it with a sort of low concentration or relatively low concentration, but strong acid, something like dichloroacetic acid in DCM. So there's a lot of organic solvents. So a lot of the sensors or electrodes from Zimmer and Peacock, if we make them on PET or on any other polymer, they're not really compatible with organic solvents, but we do have a special range of electrodes that are compatible with organic solvents. Anyway, so we wash this solid phase, and we release the trityl groups, is the idea. So trityl kind of comes out. Now you should be able to follow this using electrochemical techniques. So I put EC signal here. The reason I put that is because I have seen people do it fairly naively. But at ZP, of course, we have a bit of a speciality in electroanalytical techniques. So I think we can actually do it better than the traditional, simpler ways that people have sort of thought about this. But in general, I sort of sketch out what I would expect, that you'd get this electrochemical signal when the trityl was being eluted from that. And obviously, I would expect the signal to change when the trityl group has stopped eluting. So I think this is fairly doable. The answer is you actually, you do have to try, but I think that one can play both with the electrodes, but I think that's less useful actually. I think most electrodes would work that I would suggest today, but I think actually play with the excitation, this EC signal the generation of the signal, I think, can be done in a lot more sophisticated ways and probably more sensitive, and maybe I could also say specific as well, ways than just what people have traditionally done. I just wanted to touch on the microfluidics, because I think that if you're trying to measure a waste stream, um, this was literally developed for that kind of work. This is one of the first products we ever designed. It happens to have the wetted parts are either ceramic or glass, and the tubing obviously is PTFE, which is a fluorinated polymer. It's very resistant to organic solvents, and it was developed with the idea of actually things like originally it was kind of DMF and all sorts of dimethylformamide. I think that is solvents going down there. So anyway, it's made of organic resistant materials. But I was looking at it before talking about it today, and I was thinking, would we design it that way today? The reason I'd be a little bit reluctant is because it's got a bit of a sort of dead volume above that electrode. You know, there's a chamber there, it's about 300 nanoliters. So depending on the total solvents that are being flowed, that's either significant. Is that 300 nanoliters? It might be 300 microliters, actually. 300 microliters. I just think that there are actually better designs these days. So this is something that we just did really recently. I'll just do it again. It's so fast. You can see that the way that color changes there. You know, it's so fast, and there's really little sort of dead volume in a design like that. So I would be a little bit reluctant just to kind of go back and use what we've done in the past. I think the answer on this one is we would want to do some sort of proof of principle project around this. But I want to touch upon, I am going to make a recommendation in a bit about gold electrodes, but there I'm going to change my recommendation on gold electrodes because that will be for a biosensor application. This is really for a organic reaction following. And so here we have got a video online where we actually test these electrodes with I think acetonitrile is mentioned in the video, but I know that these electrodes are really resistant to organic solvents. They would in part develop for a pharmaceutical application when I knew that they were going to be using organic solvents. So the quick answer is we do have a range of electrodes that are resistant to organic solvents. If we were doing this work, I'm going to put a link to these under note. We would be using one of these electrodes. I don't really think the geometry matters so much, to be honest with you. There might be some nuances that would make us choose one over the other. We've got all these pack sizes out there of packs of 10, and we did an inventory count or check, let's say, just this week. And so we actually have, quite a few of these electrodes available. And I've also put a link to where these are as well. So if I was to sort of summarize this so far, I think it is perfectly possible to measure that reaction in those solvents using electrodes like this. I think ZP would have to we would like to be involved, and it would probably have to be paid program work. And I think the things we would be wanting to think about, we do have those microfluidic cells, but could they be better designed for this application? I suspect so. The electrodes are no issue, we got them. And then the last bit was we would really be wanting to I don't say play, but actually optimize the excitation of those electrodes so that we were able to measure the signal in a most sort of specific and I'd also want to say selective and sensitive manner. And obviously we have a potentiostats to do that absolutely galore. Question number 5. Somebody's been trying to make some gold electrodes, then having a problem with repeatability. These electrodes here, I don't consider them super useful for the person before. But I just want to run through it a little bit. So this is a suggestion I'm making for the person who wants to do, I think it's probably more biosensor applications. This is we use our own gold electrodes when developing bioassays. This is a bioassay where we've been making an immunotype assay. It's probably worth saying that we do discuss these gold electrodes quite in depth at our workshop. So hopefully the 8th and 9th of March in Norway, that might be something that you would actually consider coming to. And of course, we do preference people who are using our own potentiostats. But anyway, that said, what we're looking at here is 1, 2, 3, 4. It's 12 electrodes. So this is a triplicate where we've functionalized the gold electrodes, another triplicate where we functionalize the gold electrodes, another triplicate where we functionalize the gold electrode, another triplicate. These are different concentrations. You can see that we've used impedance spectroscopy here, which is slightly related to the earlier comments about conductivity. What you can see here is actually because the underlying gold electrodes are so repeatable, even though we have made these gold electrodes by hand, and when I say by hand, I should say the functionalization step by hand, they're really, I want to say, tight. And that's because the underlying, or the tolerance is very tight. It's because the underlying gold electrodes are really, I would say, high quality. We're really, really good at making repeatable electrodes. Our relative standard deviation, or our coefficient of variation, this is something that we test before shipping. It's always 4% or below, so we're really quite good at repeatability. But it's really important if using gold electrodes in a biosensor type application that you actually do clean the electrodes. Just before we use these gold electrodes, we do clean them. We obviously clean them on, I want to say on robots really, but robots are just essentially fancy hand pipetters. So I just want to make sure that you're aware that whatever you're doing, gold electrodes do have to be activated or cleaned before use. I've got some links here. I'll make sure I put those underneath the video as well. Somebody who's also interested in some platinum electrodes, but in a much smaller pack size. And there's a link here, and we have done that. So we have produced a whole series of hyper value platinum electrodes that are hopefully smaller pack size and more efficient, let's say, on people's budgets. So if I'm just going to wrap up for this week, we are able to do these wearable sensors. I think the first step for anyone really trying to engage on wearable biosensors is to come to one of our workshops. Our workshops are 2 days. They're pretty intense. You get to make wearable biosensors and test wearable biosensors. We do have the 6-channel potentiostat. It's appeared a few times today. This is a real workhorse for us and sort of tells you, and it's also, it avoids compatibility problems that people have. They're using electrodes or biosensors from us, and then we know that they will work on our potentiostats. We also touched on cortisol, cortisone, and melatonin today, saying that actually we do have a cortisol sensor. We talked about the connection between cortisol and cortisone. Really, they're just oxidized and reduced forms of one another, and also the sort of physiological response between melatonin and cortisol. That as one goes up, the other one goes down. Reaction monitoring of detritylation. So we do have, and I will link to it, those gold electrodes. They should be very resistant to solvents, but I think it really, because of our experience, it's kind of unusual in flow, microfluidics, electrochemistry, and screen printed electrodes, and materials that are resistant to organic solvents. I think it's actually best doing a project with us on that so we can bring all that experience together. We did talk about gold electrodes. Somebody has a problem in their lab of reproducibility of gold electrodes. Honestly, the ones we have are really excellent. And then the platinum electrodes we have now and made them available in much smaller pack sizes. So I just want to say another thank you to AFTAB this morning for coming along. If you have any questions of Zimmer and Peacock, you can see that we put quite a bit of effort into answering those questions. It's been 25 minutes so far this morning. Otherwise, have a good end of the week. Have a good weekend. And we will speak to some of you again next Thursday at 8 a.m. London time as part of our ZP Developer Zone webinar. Okay, thanks very much.